Next, we have Ashish Mahabal, a senior researcher at Caltech. I first met Ashish back in 2006, working on what I will call the interesting properties of the Palomar Plus camera. Since he's moved on to much better things, the Catalina real-time transient survey and its many successes, and Ashish is an instrumental in discovery and classification in CRPS. Ashish's talk today is, I'm looking at the title, it's on knowledge from extremely sparse matrices. So, Ashish.
Okay, so I'm going to be speaking about knowledge from sparse matrices, and what I mean is that we have data sets where we have parameters, or we expect to have lots of parameters, but we do not have knowledge about a large number of them and how to try to figure out what those objects are. And in that sense, it is somewhat akin to what Maya was saying, that the goal is to figure out what kind of information we need to have, what kind of that we should be able to find out what an object is based on a very small amount of data and as early as possible. So there are a large number of pieces that go into this work, and here is a list of collaborators that I have. George is sitting here, and Andrew is involved with the CRTS, Roy Williams with Skylar. And in this specific work, there is also some component that Sajid Philip from India has worked on, which I'll be coming to using Bayesian networks, plus Babak Moghadam and Mike Turman from JPL and many other collaborators. So as has already been mentioned, time domain astronomy is gaining real importance, and there are a large number of resources that are coming into the picture. And instead of just digital snapshots, what we are having more and more are digital movies, and even larger telescopes like the SK and LSST will be coming into the picture. So what we'll be having is that really hundreds of thousands of transients per night instead of just any kind of objects. And I'll be coming to what transients are. But specifically, as Peter mentioned, one data set that we are using is from the CRTS, the Catalina Real-Time Transient Survey. And there are 3 telescopes from which these data come together. And these are not very large telescopes, but the real strength is the large area that they cover every night, as much as 2,500 square degrees per night, over a total area of 33,000 square degrees, which really amounts to a really large part of the sky. One important thing also is that the data policy with the survey is open. All the transients that we find, we publish in real time for anyone to look at, and that is very necessary in this day because so many transients are being found and we cannot follow them on our own. And unless they are followed up, unless more observations are obtained on them, we do not really know what they are going to be. So this gives more people a possibility to follow them and get some science done. So this is the sky coverage from CRTS. This is as of August 2011, and it's much more now. So this represents the entire sky really, so 82% of the entire sky. And with a single pass, we go from 19 to 21 magnitudes, 3 different telescopes. And when we co-add the images, and there are hundreds of images on many locations, we can go up to 24th magnitude. So this represents really a deep sky image, and with individual images we can do lots of interesting things. So something that Tamash mentioned, for instance, in principle we could be trying that with this data set. So here are a couple of sample light curves. Here is a blazar, a radio source. On the x-axis we have got days, so this represents about 3 to 4 years. On the y-axis we have got magnitude. And one magnitude difference is about 2.5 times. So what this means is that this object, this point is about 2.5 times fainter than that object. Here is another one which is a CV, and both blazars and CVs vary stochastically. There is no periodic component to them and so on. Whereas supernova, for instance, is an exploding star. For a long time you don't see anything. The red triangles represent upper limit, so you don't know, you didn't see anything there, but based on other objects nearby you can say what was the brightest that object could have been, and suddenly you find that there is a big detection. And notice that this 20th magnitude, the 16th magnitude, so several times the brightness has increased and you start seeing that object. And this is what the classic definition of a transient is, something that has changed in brightness a lot in a small amount of time. And so here are corresponding images for those. One with upper limit, you don't see anything at the center of that box, whereas when the supernova actually exploded, you see that there is a bright object there. And those are the kinds of things that we can find easily, and the threshold is kept high so that we don't get overwhelmed by a large number of objects. We have released 200 million light curves for all kinds of sources, including the transients, but not just transients, and soon it's going to be 500 million sources. So there's a large data set out there that people can play around with. And it's not just supernovae or CVs or blazars. The hierarchy of possible objects that vary a lot is huge. And here we have a tree where we have extrinsic objects and intrinsic objects, extrinsic being where the variability comes about due to motion, for instance, or an object eclipsing another object, whereas intrinsic variability is where something is happening inside the object, like an explosion or something due to an Aegean variability. And with each of them, there are many subtypes. So the Aegeans, there are subtypes, and the supernovae, there are SN type 1A, 1B, and so on. So let me go on to some of the CRTS discoveries quickly. This is a supernova type 1A, which was extremely luminous. And there was then a supernova which went on, its brightness kept on increasing for several hundred days. Normally you see that when a supernova explodes, it's in a matter of days or a few weeks that it reaches its peak and then starts fading. Then there was a supernova which was close to the center of a galaxy, an Aegean source. And just to give you a flavor of the different kinds of objects, I'm going through these quickly. Then there are the cataclysmic variables and dwarf novae, where you have got two stars that are close to each other, matter from one object falls into the other, and that is why the other object seems to get brighter. Or there are the fast transients, where these four images, so the typical cadence of CRTS is that four images are taken 10 minutes apart. And so there was only a difference of 10 minutes from here to here, and then from that to the next, and so on. But you can see already how the brightness was changing within a matter of minutes. Or then there are various other Aegean that one finds where the brightness is changing a lot. Then we have been finding a lot of Fermi IDs with CRTS light curves. So Fermi, there are detections in gamma rays and large error ellipses. We don't know what those objects are, but using light curves one can find those out. And even planets can be found around white dwarfs, where it's the decrease in brightness that leads to let you know that there is something interesting happening there. Or young stellar objects where the brightness keeps on increasing for years. Again, remember, this is days here, so for about 1500, 1800 days, the brightness keeps on increasing. So this is overall as of March 2012, the number of transients that were found by CRTS, the three different telescopes. And there were more than 5,000 transients found. Here are a few classes that I already mentioned. Remember again that the threshold has been set deliberately high. What that means is that only the most dramatic transients were seen, and if we were to lower the threshold, there will be really a much larger explosion of how many objects that we are seeing. So given every 10 to the power 6 objects that we see, roughly one tends to be a transient among those. And the rate of transients and variables is at least an order of magnitude higher than that. We are just screening them out for now. The important column here is also the other column here, which shows that objects, based on the little information that we have, we cannot say what they are. And those really are likely to hold key to many rarer classes of objects, which can lead to a lot of new science. So that is something that one has to keep in mind. And trying to understand what those are, or trying to understand all the objects really, what we do is put together a portfolio of information for each object. So through this skyalert.org, first of all, when an object is found, a transient is found, all the cutouts for that object are put together along with its magnitudes, positions, and whatever information there is. And a portfolio started for that, so more information can be put together. And this is all public. So why that is necessary is because just by looking at the cutouts, you cannot really say what kind of transient that is likely to be. Here are three examples. This is a flare star. This is a dwarf nova, where again, as I said, there are two stars that are involved in an interaction, and a blazar. So if you were to look at just the images that were taken by CRTS, at the centers are the faint and the bright positions which get compared to find the transients. And you can see that just by looking at the images, you cannot really see what those are. So what you really need is important rapid and automated follow-up that will lead to classification. So there are two kinds of follow-ups that can happen. Active follow-up, where you schedule a telescope to go and do some observations and get that information. That can be a very pointed, very specific observation so that you understand what class that is. It can also be a passive follow-up, where what can happen is that you can look up archives from like Sloan or radio telescopes that have done the observations before of a large part of the sky, and ask yourself questions. Is it likely to be a radio source? Was there a galaxy nearby? And so on. So all those computed parameters also get added to the portfolio. And simple questions can be asked even based on just 2 or 3 points that one has. For instance, in case of a supernova, we know that the object explodes so that it increases in brightness and then falls in brightness. So normally you won't expect it to go down in brightness and then go up again, whereas these other 3 phases are possible. It can happen that the supernova goes down when it's becoming fainter, or it becomes brighter and then turns around, or it keeps on becoming brighter. So based on just a few points too, you can say a little bit about that. So it is those kinds of small bits that are put together into classifiers. And follow-up observations can be in different filters. CRTS does that with an open filter so that there is no color information there, but you can do follow-up observations from something like Palomar 16-inch telescope, and we do that from several different telescopes. That gives you additional information. So all that goes together back into this dynamically growing portfolio, and that is what brings us to the part of classification using these really sparse data sets. And sparse again because we don't have all these parameters for all the objects. We have really little information for almost all the transients, and trying to figure out what those are based on just those transients, just those information. So some simple things can be done. Supernovae, because they look somewhat different from all the other transients, that's the first step that one can try to do, separate them from other objects. Within supernovae, then there are various classes, so this can be a binary set of classifications that can go on. And then within the non-supernovae, you can separate CVs and blazars from RR, Lyra and Myra. Again, CV and blazars being more stochastically varying, whereas the others being more periodic. And then you can go down the tree to as deep as you want as more and more information comes together. So one of the methods that we have been using involves just using the DMDT dataset. So if you take a light curve which has endpoints, for each of the endpoints, if you compare its distance in time and in magnitude from each of the other points, you can build a histogram based on that. So if you were to take say 1,000 supernovae of a given type, then from each endpoints you can put together a histogram, and this is what is shown here. So for supernovae type 1a, you will get a density of this nature. For supernovae type 2p, that's a 2p actually, which is of type plateau, and that is what is reflected here. You can see the difference between 1a and 2p much easily in this density histogram, whereas an RR Lyrae, which is kind of a periodic variable, you see that the histogram is completely different. So in such a case, if you have got say 3 or 4 points of a new transient that you have found, based on just that information, you can ask yourself a question using one of the various quantitative distance measures. Is it more likely to be this or a supernova type 2p or RR Lyrae, going through the entire data set, and that is how you can say what that particular object is. Or we have also been characterizing light curves. So given a light curve, you can do a series of numbers from a given light curve, and we are using a lot of measures that the Berkeley group has presented, Richards and the group. So these features are then converted into a set of numbers, and then those numbers one can ask various questions by giving hundreds of thousands of those points. And so all these automated classification methods can be applied in feature space, and one can try to optimize those feature selection, because for specific types of classes, specific features of those, like what is the amplitude available, or if one of the light curves is periodic, one can get a period out of it, or various numbers associated with the periods, those can be obtained, those can give you the information. So then one can start discriminating between the different classes based on just that. naive Bayesian networks have also been implemented based on that. And so one can start here with various priors. This is from the bright sources from GCVS, and one can have different colors, various other observed parameters and incidental parameters, and using just these values one gets typical accuracy of 80%, typical contamination between 15 to 20%, and as one adds more parameters, that information, that the classification will improve. So again, what one is trying to make out of this is that trying to make as much as possible all of the sparse data sets that we have. So considering just the few magnitudes and the corresponding positions that we have, the follow-up colors from say the 60-inch telescope, or proximity to the nearest galaxy and brightness of the galaxy, and also similarly proximity to a nearby radio source or possible gamma ray source and so on, and similar information from other archives. So the data set that I'm describing now consists of 39 mostly absent parameters. So there are up to 39 parameters that will be available based on these, and we bin them in about 15 to 20 bins. And so this huge matrix of a few hundred, again mostly empty, is what we are using for this, what I'm going to describe now. So this work has been done with Sajid Philip, and we have used about 1200 of the 6000 transients that I mentioned, which is a subset, which included about 300 CVs, 450 supernovae, and smaller sets of other classes. And here what we mainly experimented with is how to build an optimal sample for training. This is again a Bayesian network that was used, and what is often used is something like the Wilson's criteria, where you start with a training sample. Many people use the 80-20 or the 90-10 or leave one out kind of samples, but that becomes rather random in the sense that you are not trying to select the sample specifically. So there are ways to do a selection of sample as well. And Wilson's criteria, for instance, it starts with a random sample, but then once it cycles them through the classification, then it retains only the successful ones and then includes other criteria, other samples in it, and again goes through an iteration. And it is based on that that other setups like multi-edit or citation editing have come through. Whereas what we are using here is difference boosting, where we keep diverse examples. So rather than keeping samples which have succeeded, we say that let's try to pick samples where they look different from the other objects, and then look at what the performance for those are. And the samples that succeed, those are kept in the test sample. So failed examples are the ones that get added to the training sample. And this is how it can be shown schematically for a single parameter. Of course, for multiple parameters, it becomes much more difficult and not easy to show on the diagram. So if you have got two classes and this is how their histograms look in a single parameter, then we try to choose samples which are from these regions rather than from any region here. And what that does is that we are trying to differentiate them as much as possible during the training process. So a two-class place with greater overlap, here again there is less amount available for us to choose from, but still that is still useful, because as the number of classes is higher and as the number of bins and types is larger, we can still have a large enough sample. So what one does is one starts with a flat prior, and the weights, initial weights are quite uniform, and as an object gets classified into a wrong class based on what the correct class was and what the wrong class is, and the difference between them and a learning parameter here, those weights are updated and one goes through the cycle again. So this is what we get for using the setup that we currently have. For several classes which have large number of input sets in the training sample, we get more than 90% completeness, and for the with about 10% contamination. When we go to testing, where every new transient that is seen by CRTS is automatically passed through this system, the classification goes down to about 60 to 70% completeness, because every transient tends to be somewhat different from what has been seen before. And in fact, for classes which cannot be easily parameterized, the completeness is really small, but that gets improved as the priors can be improved. And the other thing that one notices is that the confidence is fairly high for objects where the contamination is good, but as we go down to objects and classes where the information is really not present much, the predicted percentage also goes down in the confidence. And of course, there are many reasons for the confidence to be not good as well as the completeness to be not good. First of all, there are many objects for which the priors that are available are not really ideal. For all objects, actually, the priors are not ideal, but there are some classes where they are really, really bad, and that will go on improving as time goes. Then the feature descriptors of light curves have not been included yet. Those will be included. So the classification that one sees, the expert who has classified the objects, expert has access to a lot of information that the program does not, and slowly that is being added. It's not easy to parameterize that, but as that gets added, things are likely to keep on improving. Then time sense detection will also be included. For instance, when I have got 3 sets of observations from the 60-inch telescope. Now this time when this observation was done, and somewhere here when the actual detection of the transient was done, so this delta t and this delta t is not being taken into consideration, and obviously the nature of the object, or rather the observations that we are getting in different filters, depend a lot on what the delta time was. So that is being included. And a better incorporation of contextual information is also going to be done. For instance, we are taking into consideration what is the distance to the nearest galaxy. We are taking into consideration what is the brightness of that galaxy, but we are not taking it into consideration as a pair. That becomes very important because that information is correlated. So all these things are going to be added gradually. Here is a high proper motion star, for instance. This is a combined image from several epochs. You see everything else in a similar fashion. So this star is this star, and these 2 stars are these 2 stars here. But this object seems to have moved, and there's no way that information about such motions can be given unless there is a catalog of high proper motion stars present. So that information also needs to get filtered in. There are, of course, further applications to this as well. For instance, there are data sets where the time critical information is not needed, but still we can apply. And one of the data sets is young stellar objects in the Orion Nebula. So there is a data set of 2000 stars where dense light curves are available, and the same thing is being applied to them. So their information is available in as many as 7 different bands, and the light curve parameters that I mentioned earlier, where about 20 different parameters can be obtained, giving us a 140 dimensional data space. So the same techniques are being applied to those, and that's being tested right now. So I will stop with the summary here. With a large number of transients that we are poised to be finding soon, the early characterization is imperative, and selecting appropriate examples during training, like assured, may play a very important role when many parameters of these are missing. And we are implementing such an algorithm for real-time classification, which is ongoing right now with CRTS transients for follow-up. Thank you.
I am going to use my role here to ask the first question. Ashish, can you turn this around and say, when you add in these extra features that you were talking about, can you then ask the question, what is the most discriminating observation to take next that would be cheapest to, further improve your classification?
Yes, in fact, we have something that that's going on related to that, and I had a slide which I removed at the last minute, and this shows another Bayesian network related thing where we are working on something that will answer a question like that, and an earlier speaker also talked about scaling telescopes essentially. So if you have got, say, several different classes which have a certain probability, so here the vertical bars represent probabilities, the height of them, and the x-axis represents different classes. And then if you have access to 2 different telescopes with 2 different instruments, then one can easily build priors if one has enough data, and that enough data has not been gathered yet, and I will come to what can be done about it. Then one can ask the question that if I were to do a follow-up observation with this telescope, so in this case what I have is that I've got x0, and in this case I'm going to get xa, and I'm going to get xb in this case, then is it going to improve my classification? So if I do this combination of observation, then it's going to make the classification unambiguous, whereas if I do it with this, then it's going to leave it more ambiguous. So clearly it's better to use this telescope. So these priors are being gradually developed. Gaia is likely to be launched in a few months' time, and they're getting ready for a lot of follow-up observation right now. Using a lot of European telescopes, we are following some CRTS transients, and we are gathering such data to build such a prior.
Other questions?
you said in your training data set you had a 10% contamination, but I don't think you gave a number for the test data set. You said the completeness went down, but how much did the false positive rate go up?
So it actually went up because we have got a finite number of classes that we are using, and so as the completeness went down, the contamination did go up. It was about 30 to 40% actually, so it did go up.
Actually, let me ask a follow-up question to the first question. If you want to go back to that slide you just showed, this is saying if I want to follow up on this object, which sensor do I want to use?
Right.
How about if I say I'm interested in this sort of thing, which object do I want to follow up on, and which sensor do I want to use? Do you have any thoughts about how to address that question?
Right. So it is a sub-question. You're right that it's another facet of the same question. Excuse me. So why this question, why I put it in this fashion was that it is assuming that we have a list of transients which we have already sorted in importance, that this looks more interesting and where can we get follow-up on that. But your question turns it around and whether we can figure that out first. So which of these n objects should we be following first? Right?
Or alternatively, what additional information will tell us which one will be most interesting?
Right. So it can be folded in a similar fashion. So that is a similar question. Maybe you can talk over coffee break.
Okay, let's thank Ashish one more time. Next, we have Ashish Mahabal, a senior researcher at Caltech. I first met Ashish back in 2006, working on what I will call the interesting properties of the Power Northwest camera. Since he's moved on to much better things, the Catalina real-time transient survey and its many successes, and Ashish is an instrumental in the discovery and classification in CRPS. Ashish's talk today.
George is sitting here, and Andrew is involved with the CRTS, Roy Williams with Skylar. And in this specific work, there is also some component that Sajid Philip from India has worked on, which I'll be coming to using Bayesian networks, plus Babak Moghadam and Mike Turman from JPL and many other collaborators. So as has already been mentioned, time domain astronomy is gaining real importance, and there are a large number of resources that are coming into the picture, and instead of just digital snapshots, what we are having more and more are digital movies. And
I'm looking at the title, and some knowledge from extremely sparse matrices. So, Ashish.
Okay, so I'm going to be speaking about knowledge from sparse matrices, and what I mean is that we have data sets where we have parameters, or we expect to have lots of parameters, but we do not have knowledge about a large number of them and how to try to figure out what those objects are. And in that sense, it is somewhat akin to what Maya was saying, that the goal is to figure out what kind of information we need to have, what kind of that we should be able to find out what an object is based on a very small amount of data and as early as possible. So there are a large number of pieces that go into this work, and here is a list of collaborators that have even larger telescopes like the SK and LSST will be coming into the picture. So what we'll be having is that really hundreds of thousands of transients per night instead of just any kind of objects, and I'll be coming to what transients are. But specifically, as Peter mentioned, one data set that we are using is from the CRTS, the Catalina Real-Time Transient Survey. And there are 3 telescopes from which these data come together. And these are not very large telescopes, but the real strength is the large area that they cover.